Swayam Prabha. Digital India. Educated India.
Next talk will be given by my colleague Babji Srinivasan on freshwater minimization and multi-stage, multi-product batch process by trading of milk fats.
Yeah. Good morning, everyone. So I'll be talking about freshwater minimization in a multi-stage, multi-product batch process by trading of the mix pack. Okay. So again, so here's my outline. So I'll quickly go into the motivation. So I don't need to talk about water consumption, depleting water resources. Many of you here will know it. So what is something which I'll focus on is this part where the batch processes consume a large amount of water, and typically India is known for its batch processes, especially milk industry, where there is a lot of cleaning in place, and as well textile industry. So textile industry is specific to Southeast Asian countries, and India is one of the major textile industry hub, and therefore water is consumed a lot in these industries. And it has to be corroborated with the fact that India has only 4% of the freshwater resources to support 17% of global population. So in that sense, India is really a water stressed country, and we are doing more batch processes as well, which will stress even further. So in this work, I'm going to talk about batch process, specifically textile industry, and we are talking about minimization, freshwater minimization in a textile industry process by, of course, trading of mixed pack. I'll come to it. So a few literature studies. We have a group along with Toko from Witwatersrand. We have been looking at recently on this batch processes. There are at least 2 recent works in 2021 where we focused on looking at synthesizing an optimal schedule and water network based on NLP approaches, and the other one is we started off with based on GA based approaches, that's genetic algorithm. We initially started off with heuristics, that's genetic algorithm, and we moved on to NLP based techniques. And there are of course other groups who have been looking at textile industry, specifically dyeing plants, water network integration, and then optimizing scheduling in textile dyeing industry, etc. Okay, so that's about a quick literature on what has been done earlier in water space, especially in textile industries. And there are hardly any works which actually try to integrate water and energy in these industries. And specifically we are targeting like a medium scale industries where you don't have a lot of data to measure, and computational, there is not much wherewithal to implement things, and then we are therefore targeting medium scale industries where we kind of trying to use insight based approaches rather than mathematical programming techniques. This work focuses on insight based approaches compared to mathematical approaches, and water pinch analysis is one of the widely used approaches, but it has its own limitations. That is, we have streams with multiple contaminants, then we have a problem, and then we have variation of contaminants with respect to time. That also is a issue here. And mathematical programming lack to provide insight of the process. That's what we said. If it is a very well-known, established industry, large scale, you would have these information, but mathematical programming becomes difficult, due to process variables during the runtime. That is, getting detailed insights becomes a problem, and handling of discontinuities and local minima. And therefore, we are in this work, we are focusing on an insight-based approach. And what we are trying to do is, can we minimize freshwater consumption, but slightly trading off the make span, right? So it's not, we are not talking about critical products where make span is you're operating at optimal make span, but give allowance slightly for make span and thereby bring in the freshwater to be on the lower side. So that's the idea. So we introduce a concept called intentional waiting duration to maximize the make span. To maximize freshwater, reduce freshwater consumption. And what we are also focusing on, reduction in centralized storage facilities, right? So as I said, these are medium scale industries where you don't have large storage facilities. Storage facilities add cost to it, and therefore we are also, by this approach, we are also trying to reduce the storage facilities, and we are also coming up with optimizing the production schedule using GA so as to minimize the overall time horizon, but the focus is with minimizing the freshwater consumption. So this is the process description. You have a textile plant, you have knitted cloth processing unit, a woven cloth. So knitted cloth is where we are focusing on. We have a process where there is a degumming, washing, chemical treating, all of this. This is a typical batch. It operates in a batch mode, and then you have a soft, all of these processes happening in a soft flow dyeing machine, referred as the unit in this approach. So we have 4 units, that is 4 soft dyeing machine, and there are about 6 units where there are 4 products to be made with different shades: white, light, medium and dark. And there are, each of them goes through several stages, right? So what I mean by stages is, this is a unit, okay, and then let's say this is one product P1, let's say call it as white, and white goes through several stages in this, and for example, white goes through 5, and dark is the highest, which goes through 14 stages, okay, and each stage has its own water consumption, okay, the amount of water consumed in each stage is the same, and depending upon the number of stages, the water consumed is going to be larger. So dark consumes about large amount of water compared to a white shade. Okay, so this is a brief overview of the stages, the products which we are talking about, and the number of units. So this is the soft flow dyeing machine. So you can see that there are about 6 soft flow dyeing machines here, and there is a chemical and mixing dosing unit here. So fresh water is injected from the top, okay, and then discharge sump, so stage wise, and then unloading machine here. Okay, so this is a typical soft flow dyeing setup, and this is the problem we are looking at. So we have 14 stages, as I said, and then we have an idea about the maximum permissible concentration in each stage. So there is a very high concentration allowed of the contaminant allowed in the first stage, and very low or close to 0 in the last stage, right? So that should tell you, what it is, freshwater requirement may not be very important at the earlier stages, because concentration allowed is large, the contaminant is, concentration can be large, but you will require fresh water at the later stages, especially in the last stages. You would require a more fresh water, rather than you cannot, you don't have any possibility of recycle at the last stage, but at the beginning stages you could actually recycle things. Okay, that's what we are looking at. So let's go back. So the concentration, so stage wise duration is also given. So the white has the highest, and light is 499. The dark has the, since the stage is higher, so the dark has the largest it's a time consuming quantity, whereas white is the lowest. So this is a problem statement. Given the production recipes, the number and capacities of available units and tanks, the number of batches to be produced for each product, and maximum permissible threshold for each available tank. So that's what. So these are the 4 given quantities. We have the the production recipes, the number and capacity of tanks, the number of batches, as well as the concentration. That's the given. And then what we make assumptions, we make a unit is capable of producing all the products, and only one contaminant is present, and changeovers are sequence dependent, and changeover times are negligible. That's an assumption we make. And no amount of water is lost during the stage, and amount of water required by all the stages is the same. Those are the assumptions we make. And what is we do? We do determine the optimal sequence of products in each unit, corresponding to minimizing the time horizon, at the same time by introducing, we have introducing the intentional waiting duration, so that we minimize the freshwater consumption. So that's our goal to determine. And of course, in this process, we will also determine the variables: freshwater consumption, time, fluent water generated, and recycled water generated, etc. That's the what we determined, and constraints, what we have, only one stage can run at a time. Stages can only start when previous stages are over. Stages must follow a predefined order, and all products batches must be produced within the time horizon. Okay. And any product takes the same time to produce immaterial of the. So all any product will take the same time in the unit. That's the assumptions we make. So typically we have taken a simple example where I would like to produce 6 batches of each product. That's white, light, dark, and medium and dark. So we have calculated the make span for this this schedule. So it turns out to be like 2010 minutes, and per stage water requirement is around close to 3000 kilogram, and you can see the total fresh water is about 750,000 kilograms. So that's the requirement for this sequence. Okay, so now we will go about introducing the intentional waiting duration. Okay, so the solution methodology, I'll skip this, I'll directly go to the idea, the fundamental idea what we are looking at. See, what do we mean by intentional waiting duration? So you see here that a unit Q and unit P, unit Q finishes off its job, and the next unit is here. So, and unit P is actually happening, right? It's being processed. So what is this thing is this water, I mean this, and the second unit starts here for unit Q, second operation. Now, if I push this operation or slightly to the right, meaning I give a waiting time, right? So this portion, if I push this wait, to start slightly later, then what I could do is I can avoid storage, and at the same time, I could be able to recycle this output of this unit water to the next unit. So all I need is a slight waiting time, right? I mean, that's what I call this waiting duration, intentional waiting. It's not a part of the make span. You could have optimized it, you could have run it faster, but what you would have lost is you would have used more fresh water. So what we are trying to do is we are slightly shifting this to the right so that there is a waiting duration, so that one water outlet from the one system, one unit can be recycled to the next stage. And we are also aware that it cannot be infinite, and therefore we have a constraint that call it as minimum maximum allowed waiting duration, MAWD. So there is a constraint that you cannot violate. That's maximum allowed waiting duration. So let's take a case where the industry says I would like to produce this within 3000 minutes, and your optimal make span could be somewhere 2500, not even 3000. You could make it lesser. So the company is okay if you produce it at 3000, and the optimal could be 2500. What we are saying is, what will you benefit? Let's say if I have it as 3500 minutes instead of 3000, if you are able to trade off another 500 minutes, what is the benefit you will get in terms of fresh water consumption? That's the idea. So 3000, we are saying, let's say, move away by 500. Maybe you are moving away by 1000 units in terms of make span, optimal make span. But what is the benefit you will get in terms of fresh water consumption? That's the whole study about it. Okay. So this is the nutshell what we are trying to do. Okay. So of course the approach again we have used, we have used a heuristic approach, like genetic algorithm, where there is a global optimal solution, which will be the next stage which we'll be working on. So we all know about steps in GA. So here input is the number of input is the product, input of product batches, initialize the population, and then we have fitness functions. I'll come to this. What is a fitness function we used in the GA? And we have of course a model to evaluate the fitness function, and then there is a way in which we evaluate the fitness function to come up with the next population. And we have also modified the fitness function. Not just modified the fitness function, modified our crossover and mutations. Because if in a traditional crossover, what you will see is when you do a crossover in GA, you will have two child being produced from one crossover. That means your number of populations or the schedule will keep on changing. So what happens is, if this is used, the number of products will change from one solution to another. If you traditionally implement the regular crossover, then you will have number of products will change from one to another. So what we did is we actually modified, used a modified crossover operator. So where we actually swap and then also flip the genes so that you have only one parent being produced. And similarly, we have modified the mutation operator as well. And then this is my gene, and I have added the maximum allowed waiting duration at the end, so that, and that doesn't change with mutations or crossovers. So the MAWD keeps fixed. And so these are the two fitness functions. One is a regular fitness function when there is a, which is just the freshwater consumption less than the desired. So if it is, if that particular chromosome gives a sequence for which the freshwater consumption, for which the make span is less than the desired value, less than or equal to the desired value, the objective function is simply reducing the freshwater consumption. If for a particular chromosome gives me a sequence which consumes more, which has more make span than the allowed, then I actually penalize for that. So this is what the two objective functions are. So depending upon the sequence, depending upon the sequence generated by the chromosome and whether it is below the desired level or whether it is above the desired level, I have two objective functions. One penalizing for extra make span, the other one just minimizing the freshwater allowed. In a way, Z1 is equal to Z2 with penalty proportion to deviation from the desired make span. So these are some of the results. This is for one run of GA. Okay, and these are my dominant and non-dominant. So the maximum allowed waiting duration in this case, I have taken it after simulations. We have said it will be maximum is around 1000 minutes. So we have a MAWD ranging from 0 to 1000. And this is one run from GA where you can see the intentional waiting times here. Okay, so there is an intentional waiting time you can see, so that you can use the one unit output to the other for recycling. And this is my freshwater requirement, both dominant and non-dominant results. So you can see from the previous result of 7,400, 500 kg, now I'm going somewhere around 3,000, far lesser, right? And with increase in, of course, that is with increasing make spans because you have an intentional waiting duration. And most of the savings, interesting, which is expected as well, comes from adding tanks only at the initial stages. After about 3 tanks, the savings actually gives constant. So you don't need about 10 or 14 tanks for each stage water to store. You all need is just 3 tanks at the initial stages. And that's what this result tells. And then the last interesting factor before I conclude, you can also not just do one campaign, you can do multiple campaigns so that one campaign's last water, whatever remaining, can be reused to the next campaign. So in that sense, if you start with about 3,000, 30,000 kgs, you can actually bring it down to 15,000 or even lesser if you do multiple campaigns. Meaning the end of first campaign, water that is kept for use in the next stage. So multiple campaign is actually beneficial. So further saving of about 47% saving in water and 40% decrease in make span could also be achieved if you do a multiple campaign. And then this is the behavior of increasing make span. It's almost linear. Okay. And these are the conclusions. So water use strategy with the help of intermediate storage stand can be proven to be advantageous. In this case study, for every 20% increase in make span, 5% saving of fresh water. Okay. And if you take into account the knowledge of product and stage, it can guide the schedule of all the units at the same time in a better fashion. Or the work is limited for a single contaminant study, and the algorithm can accommodate multiple contaminants, and that will be our future work. Okay. With that note, I'll be happy to take any questions.
Very nice presentation. Question. Intentional wetting time, will that vary with the price of fresh water?
We have not actually considered the freshwater. That's a very good question. We have not considered the freshwater price at this moment. In India, it's very hard to quantify the freshwater usage in a batch industry. So we have taken it flat.
Yes,
but of course, it has to be tied up.
That would be interesting to see where the wetting time goes to the left or right. And
exactly.
I think that's quite interesting.
Yes.
One more quick question we can take. Yes, please.
One of the constraints is that the time horizon is not violated. Am I right? you do violate the time horizon within a certain range.
Yes,
correct?
we are violating within a certain range. In this case,
So you violate the constraint.
yeah, no, this is actually in the GA itself. We actually introduce a new in the chromosome. We have one place where we say maximum allowed waiting duration. So in that sense, I'm not violating. Now my violation only happens to me if it violates MAWD, and it cannot happen because that's the max I have kept. So instead of 3,000, I have kept it as 3,500.
Maybe just a quick one, follow up on that. Do you think there is an avenue for a hybrid kind of system where you've got the genetic algorithm providing your starting point for a deterministic model?
Exactly.
An avenue for this.
Exactly, that is there actually. We would like to, we'll discuss it offline. That's where we are heading to. Yes.
Yes, thank you.
Thanks.
In the interest of time, let's thank you again.